One more concept connected to optical isomerism is chiral center. We can say that if a chiral center is there, generally there is chance of optical activity. Chiral center doesn't necessarily ensure optical activity, but if chiral center is there, there is a high chance of optical activity. First, we'll understand the word chiral. Then we'll say what is chiral center, what is chiral molecule. The actual condition is we need a chiral molecule. In general, if chiral center is there, the molecule is going to be chiral. So what is chiral? The word chira means hand-like. That's a common thing, common definition that you get everywhere. So the meaning of hand-like is that your hand is not symmetrical. What do we mean by symmetrical? If I take a regular object, for example, if I take this, it can be cut into two equal halves by a plane. So it is symmetrical. So most of the things that are symmetrical can be cut into two equal halves. That's what we can say. But unlike this, if there is a non-regular object, then it can't be cut into equal halves. What is a non-regular object? For the example that we are taking is hand. It's a non-regular object. You can't cut into two equal halves. Now, you might think you can cut the hand like this, then this half is equal to this half. You might try to pass a plane like this, and then this half is equal to this half, but that is not true, because on this side of the half you are having the light skin part. On this side of the half you are having the dark skin part. So these two are called as dorsal and ventral parts, in fact. So the dark skin part is different from the light skin part, so they are not equal. Anyway, you can't cut it like this, because this side you have index finger, this side you have a ring finger, so it will not be equal. Nor you can cut it this way. That is why left-handed gloves are different from right-handed gloves. Okay, so this is the difference. Don't think in terms of surgical gloves. Okay, try thinking in terms of a cricket glove or a boxing glove, right? So this is the difference. So that is why people use the term chiral or hand-like, which is not symmetrical, which cannot be easily cut into two equal halves. That is the need for the word chiral. Now, applying this to organic molecules, we have observed that compounds are reference molecule in all organic molecules is tetrahedral structure of carbon. So when I take carbon, carbon has 4 different groups around it. That is 4 atoms, in methane 4 atoms. Now I am taking a methane-like molecule in which instead of hydrogens there are 4 groups, and all the 4 groups are different. Now the observation is, if all the 4 groups are different, then this carbon atom becomes a chiral center. That means you cannot cut this into two equal halves. Now I want all of you to pause for a moment and think whether you can cut this into two equal halves or not. Imagine the tetrahedral carbon atom. One carbon atom, one iodine, one bromine, one chlorine, one fluorine. Imagine this in tetrahedral pattern like this, and then think whether you can pass any plane such that you are able to cut into two equal halves. You can pause the video and check it, think about it, and then continue ahead. So this means when I pass a plane through this chlorine and bromine, on this side what will be there? You are cutting chlorine, carbon and bromine into two equal halves. But on this side there is fluorine, on this side there is iodine. So it is not equal. So when you pass a plane and try to cut, it is not becoming equal. That is because of having all the 4 groups different around the carbon, which is tetrahedral. So such a center is called as chiral center. Generally chiral center or chiral carbon atom we mark by an asterisk. Okay, it need not be only carbon, it can be nitrogen, oxygen, sulfur. Necessary condition is it should have 4 different groups, like all these 4 groups are different, not the same. And also the atom should be sp3 hybridized. If it is in one plane, then you have an advantage, you can cut through that plane. Each atom will be cut into half, then it is no longer chiral. But if it is tetrahedral and sp3, then they are in different planes, which means you cannot pass it through one plane on all the 4 atoms. Only 2 atoms can be cut through that plane. Remaining 2 will not be cut, which makes it chiral. The molecule is now not symmetric. It need not be carbon. For example, if I take a nitrogen atom attached to 3 alkyl groups, 4th alkyl group also I am attaching, or 4th group I am attaching, where the lone pair is donated by the nitrogen. Now this is anyway tetrahedral. Nitrogen holds a positive charge. It is called quaternary ammonium ion. Here the nitrogen is chiral. Look at this carbon. I want you to observe this example carefully. There is iodine, chlorine, bromine, and some other group. Instead of an atom, there is a group. You can take this whole as a group. So 4 different groups are present around this carbon. So it is chiral. Take this carbon, 3 groups and some other group which is different from all of these groups. So it is chiral. In this case, 2 chiral centers are present. Now, just to give the 3D view of it in 2D, I am using a wedge representation of the atom. Earlier I have explained what wedge representation is. So this carbon atom is on the board. Whatever I am representing by simple line is also on the board. So this carbon atom, this hydrogen atom and the bromine atom are on the board. Then whatever I am representing by a solid wedge is out of the plane of the board, which means it is like this. That is what is a solid wedge. It is like this. Whatever I am representing by a dashed wedge, the orange colored one, which means it is into the plane of the board, it is like this. So if this is the carbon atom, the fluorine atom is towards you like this. The iodine atom is away from you like this. The hydrogen atom is in the line like this. The bromine atom is in the line like this. That is the tetrahedral structure. Okay, so you can see these 2 angles are 109. These 2 angles are 109. Any angle is in fact 109. Okay, so this is 1V, this is 1V like this. That is the structure. Now imagine a mirror image of this. That is, the fluorine is like this, iodine is like this. There is a mirror here. Now the opposite image of the mirror looks like this. Fluorine is like this in the mirror. Do you agree with that? Because this was fluorine. Fluorine is like this. And iodine is like this. So in the mirror, iodine will look like this. So the fluorine and iodine face the fluorine and iodine like this. Hydrogen was here. Hydrogen is again going to be here. Bromine was here. Bromine is again going to be here. Now I have 2 molecules. What I am trying to tell is, because there is a chiral center, these 2 molecules have different configuration. What is configuration is a question that earlier people asked. So the configuration is different. Because of this molecule, I cannot exactly place it on that molecule. That means they are different molecules. How? You have to mentally twist this fluorine and iodine and place it here. So this is hydrogen and this is bromine for this group. So if I want the bromine to fall on the bromine, what should I do? I should take this molecule and do a 180-degree rotation like this and place it here. Agreeing with this? So hydrogen was here, hydrogen falls on hydrogen. Bromine was here. If I do a 180-degree rotation, the bromine comes here. But now let us see what happens to fluorine and iodine. For this molecule, this is fluorine. Whatever I am holding the stick in this hand, that is fluorine. And this is iodine. After the 180-degree rotation, where is the fluorine? Inside. Where is the iodine? Outside. But this diagram represents fluorine is outside, iodine is inside. So am I able to place the molecule completely on this molecule? Whatever twist I do, I will not be able to place it. That means this molecule is not superimposable on this molecule. Do you agree that there is some difference in these 2 molecules? That difference is called as configurational difference, because the orientation in 3D space is different. The only option, if I want to make that into this, is I have to break 2 bonds and rejoin it in the other way. So that means there is a configurational difference. So because there is a configurational difference, and when light passes through this molecule, it changes the direction of the molecule in one way. When light hits the other molecule, it changes the direction of the molecule in the other way. That makes one of it as D, one of it as L. This is the change in the optical activity. In that way, these 2 are becoming optical isomers. Just an add-on point, if they are optical isomers and they are mirror images of each other like this, we have a term called enantiomers. We'll speak about them later. Okay, so this is about difference in the configuration. This is about chiral centers. So this difference is happening only because chiral centers are there. Understand? If it was not a chiral center, I will point out in that way also. If it was not a chiral center, imagine two groups are same. Instead of iodine, this is also fluorine. Instead of iodine, this is also fluorine. So now all four groups are not different. Then the compound is symmetric. How do you classify it as symmetric? This is iodine, this is hydrogen, this is bromine. If I cut through hydrogen and bromine, this side also fluorine is there, this side also fluorine is there. I am able to cut into two equal halves, it becomes symmetric. So no longer this center is chiral center. So then this molecule becomes superimposable on the other molecule. How? Look at this. This is also fluorine. So since they are same, I am not using the sap. This is also fluorine, this is also fluorine. When I twist it by 180-degree rotation, this is also fluorine, this is also fluorine. Fluorine falls on fluorine. Anyway, hydrogen and bromine are representing each other the same. So that means they are superimposable. That means they rotate through plane polarized light in the same direction. They affect the plane polarized light in the same direction. So there is no change in the optical activity of both of them. So that is, so for optical activity to be there, we have understood that there is requirement of asymmetry in the molecule. That is what we call chirality in the molecule. And in general, if chiral center is there, there will be chirality of the molecule. There are other cases also, but if a chiral center is there, there will be chirality. As far as most of the organic molecules are there, we are looking for a chiral carbon atom, which is the chiral center concept.